Well, we used to have that back in grade school. You remember the bell would go off?
It's funny, in high school they switched to the simulated bell, and it's like a it felt like I was on an airplane and I had to fasten my seatbelt. I wonder how many heart attacks were caused by those tolls. Heart attacks.
All right. Let's continue with what we were doing last time. I've got a 2-story frame. And I'd like to solve for the maximum shear at G, G being in the middle. In order to solve for the maximum shear, I'll need to know where to put the loads. I'll need to know what spans to put it on. So probably the best way to go about it is to draw an influence line for the shear at G. Yes, sir.
When you're asked for the maximum shear, is that you always do like the positive shear?
Well, if you didn't say otherwise, you'd probably say yes. Right. Because if he wants negative, he's pretty sure to write neg down there. Due to the symmetry of this thing, it's probable they'll both be the same number, but yes, I would say so. You have the right to ask.
Okay, so G's in the middle.
G is in the middle.
Okay. I was going to say, 'cause if it's towards the side.
Yeah, then it wouldn't. Yeah, then there'd be a different number for minimum and maximum shear, yes. Or largest negative and largest positive. All right, so what I'm going to do is I'm going to ease up on this thing a little at a time. I'm going to come in here first and I'm going to fix all the joints. I'm not going to let them move up, down, left, right, rotate, anything at all. It just confuses me. And then I'm going to take the member out and I'm going to take it home and I'm going to put a unit kink shear at G. And so far my influence line looks like that. But I know that on this end it must come straight out of the wall at a 0-degree angle, as long as I haven't released this joint. And it's supposed to come into this wall straight, as long as I don't let this joint roll, because that's a 90-degree angle between the vertical member. And so what I'm going to do now is I'm going to push it into place. Now, when we had statically determinate structures, you took your influence line, which was not yet properly positioned, and you simply rolled it into place. No forces were required, you just eased it on down. In these, you're going to have to force it into position. It's not going to like it. It's going to bend. It's going to twist. It's going to do all kinds of things. But you should be able to take a piece of wire that looks like this, that belongs in this socket and this socket, and make it fit. So I would bring it down like this. I'd bring it like this. I'd bring it like that. And I'd see what I have to do. I need to maybe open up the walls a little bit, pull this thing down until it looks like this. You don't have to be perfect. That's kind of my guess as to what the thing looks like after you take your hands and you push the right end down with respect to the left end and slide it back in that groove. Some people like to think about it as doing it a piece at a time. So they'll take the unbent or the bent piece, the kinked piece, and they'll do nothing but pull that down to there. That brings that down to here. And that brings that on down to here. And then I say, oh, it looks good to me. And you say, well, no, I don't think so. This is okay. That end's okay. But this end is not coming into the wall. It's 90 degrees away from the wall. So you're going to have to put a moment on it in this direction to make it line up with the hole. And that's probably going to pull that down. Going to pull that down. And therefore, I would say this is your final influence line. And it is practice mostly. It's just getting used to it. It's getting used to seeing what's going on. And even now, we're not finished. Because now that I know what the influence looks like, if these two ends don't rotate, I can draw it in here. But then I notice that on this end, this member is curved down and to the left. And there's only one way to make a piece of steel like that curve like that, and that's if you have put some moment on it. You cause some moment to go this direction on it to bend it down. But there's no moment on this side, and therefore I think that when this thing gets pulled down, it's going to tend to rotate this joint. And so now that I'm going to roll the moment in the direction that it's concave. In other words, if it's concave down on the right, then I'm going to put a moment like this on the joint, because that's what this piece of steel is doing to the joint. And so it's going to rotate a little bit to the right, going to rotate a little out. On this end, it's going to rotate towards the concavity, up and in. And then, of course, we still end up with a 1 in between these two things, regardless of how many times we tinker with it. In other words, to see what the shape is. And is this shape as good as that shape? Probably so. I can't get numbers off of it anyway. So I feel this end has rolled clockwise. So I'll go ahead and bring that to here, and I'll bring it straight in. And I'll bring this one down, and I'll bring it straight in because you didn't let that joint roll. But when I see this thing is concave, I know that it's tending to roll the steel joint in the direction of the concavity, this direction. So there's probably a little bit of releasing on that one. And this joint rolls counterclockwise. And this one, I had to bring it straight in, which caused it concave on this side. This one also is going to roll counterclockwise. And then I'll finally fit this in, and the difference in the curves won't be enough to make a hill of beans, but I've kind of admitted that this joint rolls. Here's what comes out of the other end. Here it comes straight in. Here's what this member does. This one rolls. Here it comes straight in. Here's where this one comes in. And so this guy here is going to look like this. Except, now then I see there's some concavity on this side of that member. The only problem with that is this joint can't be rolled. So if you think that this member is bent, then probably what's going to do is the whole mess is going to move to the left somewhat. And so I'll take a little of that out, and I'll take a little of that out, and probably the joint has moved to the left, and the joint has moved to the left. And basically what you're doing is you're just trying to see what happens as you move through the structure because of something you did back here. Now, does it not matter if you don't get this one and instead do that one? Not really. But anytime you move these things, they usually cause movements every place else. By the same token, this member is bent and probably would like to do some unbending, and so it probably throws this joint here somewhat to the left also. Now, somebody asked, can you do this with a computer program? Yeah, you really can, and it's not that hard. What you do is you do the same thing that you and I just did. You take the original structure. If you've been asked for the shear at that point, you remove the capability for shear at that point. And you replace it with a bunch of wheels. Those wheels will still allow you to get axial force through that point. They'll still allow you to get moment through that point. And all you do is you add another joint into the structure. Another node. The computer programs will usually let you put any kind of a node you want to. And then in the computer program, you'd push. Say I want it to go down on the left. You'd have it push down on the left. You put a load in there. And up on the right, you haven't changed the static equilibrium of the structure as long as you make this the same number as this. Usually you put whatever load it takes to get a deformation diagram that you can see the deformations. And then you just tell him to do all the work, and he does all the work. And this thing goes up. Oops, I'm on the wrong floor here. That's good enough. We'll do it on this floor. This side will go up like so. This side, and it'll go down. This side will go down to here. That side will go up. Because that's kind of twisted this way, that's going to tend to cause the joint to roll in the direction of the concavity. And so it'll roll a little bit like this, and he'll just give you the whole thing. He'll show you what it looks like. He will even tell you numbers, but usually the numbers are not what you're really looking for. You're really looking for, if you want the maximum positive shear, the main thing you should do is put all the people on the right-hand side from G to D. The wind loading you don't have any control over anyway. And on this floor, you probably would put load somewhere across the right-hand half of the structure. Close enough. Could you put it on where? Yeah, I'm looking for positive shear, so I'd put it under the positive influence line. Oh, wrong side. Thank you. No, you need to holler when I goof up like that. Thank you. On the left side. Now, will it matter? It probably won't, because by the time you get down to here, these deformations they get pretty small. As you go away from where you put the disturbance in there, the distortion, the kink, it doesn't take long for these things to die out. All right, let's say I was asking for a bending moment on the same frame. In order to find the maximum positive bending moment at G, we would come in here and take the member apart, and we would remove its ability to take moment. And therefore, you would crank a unit moment in there, and that would cause the structure to turn into its own influence line. Now, this is the way you do it on the computer. And you would crank on this side, and you would crank on this side. That would cause this thing to go up. Let me check and see if I like that. It looks a little funny. Cranking on it this way means cranking on it that way. That's correct. This kind of a moment on this left end, or the right end of the left-hand member, would cause it to go up. And I'd like the influence line to go up. And then, because this thing cranked on the joint, it would probably roll the joint towards the concavity up a little bit. So that would start looking like that. And this one would go towards the clockwise direction. So it would look like so. Probably. 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 And you get your best guess as to the influence line. Is it harder than beams and things? Yeah, no doubt about it. They make a lot more sense and they're a lot easier to do. But it's still useful. Now let's say you had a statically indeterminate beam. And let's say you want the moment at this point. I would take the structure home and I would put a kink in it. Now I say that beams are easier than what we just did. We haven't really done any beams that were statically indeterminate yet, I don't think. There's my influence line. I'll admit it's not properly positioned. Got some work left to do on it. First, there's a hole in the beam right here. Seems to fit nicely on that joint. Here's a hole in the beam. When I brought it back, I was able to put those two pins in there nicely. Here's the hole in the beam. Here's the hole in the beam. And here's the hole in the beam. Those last three, not good. They're not working very nicely at all. So I would get a hydraulic jack, and I would take that joint, that hole, and I'd push it up to there. And when I push it up to there, my guess is it's going to look like this. And this side here is going to roll down. That's my guess as to what happened as you put 1 kip, 2 kips, 8 kips, 11 kips, 42 kips, 173 kips, and finally this hole lined up with that pin. And this is curved, and this is curved, and this is straight. And then I put the pin in there. And now then, I go get a hydraulic jack. Well, I'll use the same one because I got the pin in there now. and I will push this up to here. He got away. How about that? And as you push up on this, I think this is going to bend up, kind of like that. I think as you crank this thing up here counterclockwise, you're probably going to be lowering this piece right here. It'll come down, and probably it'll start looking like that. In other words, cranking this way with this piece of steel by pushing this joint up to here, cranking on this piece that used to be that high in the air, it's going to lower it down to somewhat of a lower elevation. Can I just leave it alone where it was and say what I drew you was the second position anyway, you just never saw the first? Sure. And now then the structure looks like this, and this piece is straight. And there's a hole in the beam, and there's a pin, and the two don't meet. And therefore I get a hydraulic jack, and I push down until that goes through there. Now, probably it's pretty far off, although it doesn't change what I need to do. The truth is, if this goes up 6, whatever it is, this probably is only going to be maybe a 1. These things just damp out very quickly. And if that's a 1, this is probably a 0.01. So invariably when you do these things, as you get further out, these things here are usually always thought to be bigger than they are. But it doesn't change what I'm going to do, because when I'm asked for the maximum positive moment in span BC in the middle, I know where to put the load. I make sure that we get all the traffic off of this section. I make sure that we put uniform loads all the way across here. And I make sure we put uniform loads all the way across here. And every place else, as I run my computer program, I don't put loads. Now, I do put dead loads. I put dead loads everywhere, because dead loads are the weight of the structure itself, and that's not subject to the whims of where you'd like to put loads. The dead load will go all the way across, and the answer would be this area integrated into that area, and this with that, and that negative with that, and this positive with that. And then when you added the live load contribution, you'd have only the live load integrated with this, and only the live load integrated with this. But again, the whole purpose of this is so you can tell me where to put the loads, where to put the live loads. All right. Now then, I'm going to show you a beam. "18 feet long, 18 feet long. It's got a load across the top, 1 kip per foot. And I would like to get an approximate solution for the reactions on this thing. One of the ways you can come up with a reasonably close approximation of the forces and the moments and the shears inside of this thing is to assume a point where there is no moment, a point of contraflexure. Now, I could tell you that I think the answer is, let's take out the middle support and see how bad off we are. Well, whenever you do that, you're horribly off. And almost always then you have to come back, put a force on there, and force this deflection to be zero. But surprisingly, the answers, it's a lot easier to guess the answers if you just come in here and say, I think this thing deflects like this. Due to symmetry, I don't think that joint rolls at all. And then I think it kind of comes in and deflects kind of like that. And if I ask you where is a point of zero moment, you would look at your sketch and you would see it's deflected up, bent up, and in this region it is bent down. And you'd say, well, I don't know, my best guess, I guess, be right about there. Right about there somewhere is a point of zero moment. And so I run over there with the welder, and I have him cut that joint open and put a pin. And so that all of a sudden your structure has now become statically determinate. The reason being, it is 1 degree indeterminate as it stands. In other words, if you take off this reaction, it would bend and it would behave somehow. It's just the fact that if you take off the reaction, it's so bad that you just don't have a chance of saying, close enough, let's give it a try. But putting that pin from this sketch is relatively accurate. Again, it's not going to do as well as a computer program will do. But what they really use this for usually is, even in using a computer program, you have to tell it what members are in the frame before you start. And you say, well, I don't know what, if I knew what members, I wouldn't need you. And he says, I'm not going till you put some members in here. And you say, well, all right, just put everything as a W12 by 50. He says, fine. And he runs it then, because he has the members, and he finds out half are horribly overstressed, half are horribly understressed. And you go back in there and you say, okay, make these smaller and make these bigger. Good morning. Howdy, Getman. Somebody called the other day from Toledo. He's watching the class along with us as we go. He says, who the heck is Getman anyway? Yeah, he's a celebrity. So what I'm going to do is I'm going to try and outguess where this point is. You can move it slightly, and it doesn't make too much difference. I'm going to make a statically determinate structure out of it. I'm going to find out what forces act inside of that structure. I'm going to pick the members right quick, and then I've got a pretty good first guess to go into the computer. In other words, rather than saying I want a W12 by 50, and he comes back and he says, well, it's pretty sad, you need a W36 by 290. And I say, well, okay, put a W36 by 290 in there. And then he comes back and says, well, too bad, you only need a W30 by 180. I say, well, for crying out loud, make up your mind. Put a 180 there. Says, sorry, a W32 by 192. In other words, every time you make a change anywhere in the member in a statically indeterminate structure, that stiff member invariably sucks load towards it and relieves the loads from some of the other places in the structure. And so it's just like it's a zoo, trying to get it all to settle down. And you will finally. But doing this first lets you pick a pretty close first guess as to the member size. Now, as to where that joint should go, I won't show the book, the copyright book, but I will tell you that if you have a structure that doesn't roll on one end and is propped on the other end, people have solved for the point of inflection, and it's right there. 0.25 L. Now you know how they did it. They took a cantilever beam without a support on the end. They found out how much it deflected. They then put a unit load back up and some multiple of a unit load until they got the reaction out here on the end to close that gap. And then they knew the reaction at B, and they knew the load W, and they wrote an equation for deflection and slopes and moments, and the moment equation came out 0 at a given point, and they wrote it down. Let me show you another case that they have widely worked on. Fixed on both ends. Comes out of the wall straight. Due to symmetry, it has no slope in the middle. Comes out of the wall straight. Looks pretty good to me. Where would you say the points of inflection are probably located?
Quarter.
That's exactly where they go. Kind of due to a dual symmetry. There's a symmetry about that, and there's a symmetry of this half with that half. And it comes out. Is that right? That's not right. Sorry. It does look symmetric, but it's not. Because the moments aren't the same on the end as they are in the middle. But not far off. 0.21. And 0.25 is a good guess. But, you know, somebody's already refined it better than that. Incidentally, I'm getting all of this off of page 606. He has all of these cases. They got these answers for this point of inflection just like in the previous case. They did a cantilever beam. They took everything off the right end. They came back with a unit load and made this go back up to 0, and they put a moment on it to make the slope equal to 0, which is what they wanted. And they found the location of where the pin could be put. Now, if you come across this case, pretty obvious where the pin's going to move to. Where's the pin move to? Draw the deflected shape. Where does the point of 0 moment shift to? Halfway down? Well, see, it's pretty badly curved right here. Shifts to the ends. So I can almost assure you of one thing. These pins are going to lie somewhere, a fixed case being about a 0.21, and a propped from the fixed end being about 0.25, and 0 on one end being at the 0, is going to probably be somewhere between about 0.25 and 0. It's going to be somewhere in there. So let's go back to our case. Our case actually is this case. In other words, our case, just due to symmetry, because there's no rotation of this joint, is the same thing as calling this point A, calling that point B, calling, already called it a B, calling this point A, calling that point B. You got to watch. You going to be awake? Can you give me about a 10-minute warning at the end of class? Okay. I want to let you go early. I know he'll stay awake now. Then what I'm going to do is I'm going to show you a structure with pins. They're my pins. I don't guarantee 100% accuracy here, but I guarantee you that it's a pretty good first guess as to the forces acting in the member. how many pins I need to introduce. I need one for every redundant. So if you look at the original structure and tell me that if you would take off just one support, I can give you all the answers, then I'll say, not a bad deal. But unfortunately, when you take off any one of these supports, the thing is so badly distorted, not to the proper shape, that we won't be able to live with just stopping there and taking the answers. So what I'm going to do is I'm going to come down here and I'm going to put a pin. And that pin will be at, is this our case? Pinned fixed. No, that's not our case. Pinned fixed, fixed, not our case. Pinned fixed, that's our case. If you got it wrong, you wouldn't be far off. But I'm going to put 0.25L. I'm going to put the pin. Got your calculator? What's a quarter of 18? Half of that's 9. What's it, 4.5? 4.5 feet. And 4.5 from 18 would be 13.5. And 18 feet. And reaction at A, reaction at B, reaction at C. Now, if you're really watching, you're going to, in your mind, say, wait a minute, you hadn't done anything different than I did. All I was going to take was, I was going to take one reaction and throw it away, and that's all you did. You took one unknown, namely the moment at that point, and you pretended you knew it. You threw it away. You threw away the moment at that point by causing a pin to be there. And you're right. And the structure is loaded with 1 kip per foot. And that's A, B, C. I'll call this point D. Here is a free body of member A, D, and it has a load on it. 1 kip per foot, 13.5 feet long. And here is a free body of the right-hand side of this structure. Shear at D. There's the pin at D. Here is the reaction at B. And here is the reaction at C. Got a uniform load across the top of it. 1 kip per foot. Distance, 4.5 feet, 18 feet. So I have turned your statically indeterminate structure into 2 statically determinate structures. And the only error on mine is how accurately was I able to place the pin. The error on yours when you took loose the center reaction, yeah, I know, I told you to do it, was horrible. You turned it into this structure right here, 36 feet with no support in the middle. I mean, that's just really wrong. And you fixed yours, I'll certainly admit, but I'm telling you that mine here is probably not far off. And I can make a first design with it in order to put those numbers into the computer program. Yes, sir.
Why did you put that pin a quarter of the way from that?
I cheated. Do you see in the original structure how the structure was? All right, turn it off. Jeez, man. Yeah. I bet if you hit the talk to play, somebody on the other end would say, "When you coming home, sweetie?" All right. What were we doing, Gedman? I don't know.
I asked you why you put that pen a quarter of the way.
Oh, yes, thank you.
That model that you have, it's a fixed support and a pin, but you have two pins.
Well, all right, but first off, do you agree that if you look at this half of the structure, first off, that this joint in your two-span structure doesn't rotate due to symmetry? So what I'm telling you is we basically have a fixed pinned beam. And then I cheated. Then I went over to the book and I looked up fixed pin beams right here. And I saw that for that case, someone had worked their tails off finding the solution for the reaction at the pin and finding where the point of inflection is located. And so that's where I put my pin. All right. So there we go. This is what I'm looking for. Got your calculator? 1 times 13 and a half times 13 and a half divided by 2. 91.125. Thank you. If someone else will check him, we'll be happy to take a correction on this. Otherwise, you'll find out it's wrong when you get home. I mean, I only got one helper here, and I'm just glad I got at least one. One times 22.5 times 22.5 divided by 2. To that number, add 91.125 times 22.5 equals, and then divide the resulting moment about C by 18.
127.97.
Thank you. Some numbers down on the end that I don't care about, obviously. From the 127.97, subtract 91.125, and from that subtract 1 times 22.5. 14.35. And if you would, add 127.97 plus 14.35 minus 91.125 minus 22.5. 0.7, just a plain old. Now, what do you get? 98. Okay, well then maybe this reaction goes. Can't imagine it going down. Oh yeah, with the 91 on there. No, that reaction shouldn't go down, no matter what we do. All right. I'll just get some people to help us here. I may have given you a wrong number. Lane, got a calculator? Lane?
I'm not Lane, my kids are.
Oh. Marshall, you got a calculator? Everybody get your calculator out and solve for these reactions for me. When I call on you, you, by golly, better have me a number. Did we get these here right? Something's wrong here. Something's wrong here. See, because it's only 13.5 total. So here's the problem. I probably some moments about this point, got the moment, and then forgot to tell you to divide by 13 and a half.
It's 6.75.
Thank you. That's the problem. So 6.75. In fact, I think I remember, I didn't even think to tell you, then divide the moment by 13 and a half. All right. Now we're cooking. The assignment still is, you better be able to solve for the reactions on a beam. You may say, well, you can't solve for them. Yeah, but I already killed my people. The lawyer already took care of all those problems. I'm just trying to make sure you don't. Bustamante, what is the answer for the reaction at B? What do you mean, my phooey, No. Bustamante. I mean, when there's nothing going on, when you're not even punching numbers, I know you're just blowing me off. Morrison? 33. Right on the money? That's a little unusual. I'll be dang. At least he didn't make me write down a number I had to erase. Got to pick out who's not going to pass this class early, because it's always good to know ahead of time. Morrison, you're still not working on it, huh? Don't look away. Don't look away. Yeah, I can see we're not going to get out of here early. R sub B, somebody. Thank you. 22.5, thank you. And 6.75, thank you. We say it's 6.75 until you decide it's a different number. And then we'll listen to you. Who thinks it's 6.75? Well, yeah, but you three are all really together there. That's a hard sell. All right, now we're ready. It worked as a team. 6.75, 6.75, 0. 6.75 down. 1 times 4.5 more. 4.5 more on this is 10, 11.25. 11.25 kicks up 22.5. 11.25, thank you, sir. 11.25 minus 18. 6.75. Thank you. Closes on 0. Moment diagram. Moment diagram is the area under that curve. Is 1/2 the base times the height. What's 6.75 times 13.5 divided by 4? How many? 22.78. Thank you. And this moment continues on down, and then it goes positive, and then it goes negative. And we'd have to find the location of that point. The whole point being, not a lot of time involved to get a estimate of what the maximum moments are in this beam, and then go pick a beam and put that in the computer program, and then have him come back and tell you the truth. But you've already wiped out 5 or 6 iterations of trying to guess at what to put in there by getting a good start to begin with.
So in all cases, do you take a pin? Do you put pins in?
Yes, by this method what you do is you assume that you know where the point of counterflexure is. You got this number here? 40.5. Thank you. And then this one. This will be 6.75 feet right here. So it's 6.75 times 6.75 cut in half. It's about 18 or 20. 22.7. Thank you. And therefore we would design the beam to resist that moment, because my guess is they're going to use the same beam all the way across. You'd use stress is equal to MC over I is equal to M over the section modulus. That says the section modulus is equal to the moment you just got divided by the allowed stress. You'd go in the book and you'd pick a beam. All right, now then I'm going to change it somewhat. I'm going to leave that at 18 feet. And I'm going to extend that. I already worked one out here. 24 feet. Now what I'm going to do is I'm going to sketch the deflected structure. I'm going to tell you there's no rotation at this point. And you're going to scream and holler. And I'm going to say there's no rotation at that point. And I'm going to tell you it's fixed. And if that...
Is that from
Symmetric.
I told you you'd holler. Did I tell you you'd holler? See, here you started already hollering. You say that's wrong. If they want the same length due to symmetry, you can't say that anymore. I think I agree with you. So then this is joint A, joint B, joint C. Now the reason I know this didn't rotate, because I sent Joe out there with a wrench and he's cranking on this thing like crazy when this thing wanted to roll. And I said, okay, we're going home. He says, wait a minute. He says, I'm going home too. I'm letting go of this wrench. Once Joe stops holding this thing square with the world, which way is it going to roll? It is going to roll clockwise, because there's more moment on this side than there is on the left side. I agree. Now my old pin, when I had Joe out there, was at 1/4 of L. Since you have cranked clockwise on this end, which way do you think that joint, that zero moment point, moves? Up? Well, no, that's no fair. I don't mean up and down. I meant left and right. To the left. And I think you're right. But let's just see. Here is a simply supported beam where we know where the joints have zero moment, and under the action of a load it would bend down, and the pin would be there and the pin would be there. And if someone came into your beam and cranked on it more clockwise, then the thing would go up like this, and if you crank on it hard enough, it would actually have some reverse curvature. Your point of zero moment would indeed travel to the left. And that has to be because if you'll notice, when you cranked clockwise on that joint, here's the end of your beam. When you go clockwise, you cause tension on the top, compression on the bottom. And so when you put a moment on the beam in that direction, that is a negative moment. Therefore, when we get down here for you to draw your moment diagram, you're going to have some negative moment. Then this part here will still be mostly positive moment and then back to zero. But your point of counterflexure, your point of zero moment, does move away from the joint when you crank on it clockwise. By the same token, this guy's quarter point will move back slightly. How much? I don't know. Some. I just want every little bit of accuracy that I can get in here.
Is it like the ratio of the lengths?
Well, the moments are the ratio of the length, but how far the joint travels, or the 0 point of moment, isn't proportional to the two lengths. And I forget what it is now. But you're going to have to guess. And so if it was at 0.25, I'm going to tell you the new point for this case is 0.3. Why not 0.29? It's fine with me. I'll go with 0.29. Because that guess is probably just about as good as my guess.
So if you're just guessing, then
I am.
why not use the ratio of the lengths as like a more...
Well, it doesn't come out. Well, I wouldn't argue with that. I'll never even know that you use that. That'd be fine. So what ratio are you going to use? 24 over 18? What's 24 over 18? Kind of big. 1.33. And so what are we going to take 0.25 times 1.33? I don't know. I mean, I don't know either. Well, nobody's proposed it before. I mean, I've never seen it. That's how come I don't think it's probably somebody's first choice. 1/3, 0.33? Doesn't look that bad to me. Try it. We'll call it the Getman method. All right. You still see what's going on. What's going on now is I have a structure that is broken at that point with a pin, the reaction on this end and a shear on that end, and has a uniform load across it of 1 kip per foot, and this is 0.7 L. What's 0.7 times 18?
12.6.
It's 12.6 feet long. And I have another structure that looks like this, and it has a shear on it, and it has a uniform load on it, and it has a reaction at B and a reaction at C, and I can quickly give you the maximum moments, and I can go pick an initial beam and stick it in the computer. Now, one thing students always seem to think is, you know you're wrong. I do. You know you don't know what you're doing when you pick this. That's true. So you know these numbers are not correct. I really do. And then the beam you picked probably isn't correct. That's right. But then you got to stop saying I'm wrong. Because at that point, all I've done is put in a very close first guess as to a beam that might work. When I put this in the computer, then, he doesn't do this 0.3 thing. He really solves for the real shears and moment in the beam. And he may very well come back to me and say, who designed this stupid beam? I said, well, I did. He says, well, you're way off. It's overstressed. That's okay. I'm probably only going to have to make one more guess to finalize the answer. I'll make the beam a little bigger, and it'll do the job. But doing this first is a good way to get started. And not only that, after you get the whole thing done and you get a beam, a lot of times they'll have people do this just to see if the answers look reasonable coming out of the computer. because you can get some really weird answers out of a computer if you got some erroneous input data. Yes, sir. Absolutely. As a matter of fact, there is a point of inflection on the other beam, and it's right there. And so I don't care which beam you put the pin in. You would only want to do one, of course, because otherwise it won't be stable. In other words, if you put 2 pins in there, you've released 2 redundants, and you only had 1 to begin with. So yes, you could have put it on the other side. Incidentally, the one that you and I just did, 18 and 24, put the pin in the 18-foot side. If you'll look on page 607, it is exactly the same problem. The only difference is he did exactly that. He put the pin on the 24-foot side of the structure, and he got some intermediate answers. I'm sorry? Well, in his case, it was 4.8 feet out of 24. So he put his pin 4.8 feet. Trying to remember. See, in his case, his .25 number backed off to something. So 4.8 over 24 is, what'd you say, 0.2? Well, yeah, that's probably, that's what he did. He moved it from 0.25 back to 0.2 and hoped for the best. All right. All right, Quiz B coming up when? Coming Tuesday? Can you do this? I will be able to draw a structure and ask you to draw me a legal released structure or primary structure for analysis. But if I actually want you to analyze one, I'll have to give you what I want you to work on, because otherwise everybody and his brother will pick out something different, and I'll never get it graded. So I'm going to tell you that this is the primary structure that has been selected for analysis. Thank you. The person analyzing this structure called this, incidentally, it is statically indeterminate, 1, 2, 3, 4, 5, 6, 7, 8, 9, to the 9th degree. And he called this R1, and he called that a positive if R1 goes in that direction. R2, R3, R4, R5, R6, R7, R8, R9, and he asked for how many minutes I got left? Before the end of class, or before you're supposed to tell me I got 10 minutes left? Phooey. All right. Well, this was going to be Quiz B. But I can make up 1,000,000 of these, believe me. I want to know delta 1, and I want to know delta 2, 9. That was a couple of the things that I had planned on. You know how to get delta 1? The deflection in the number 1 direction due to the real loads. In other words, you're going to draw a moment diagram with the real loads on it. And to get the deflection in the number 1 direction, you're going to put a unit load in where at? The number 1 direction. And you're going to integrate MMDX over EI, or you'll use volume integrals. And 2,9 would be where you put a real unit load at 2 of 1 kip, and you put a dummy or a virtual unit load at 9, causing 2 moment diagrams, and you integrate MMDX over EI. If you can't do that, you better come see me. All right. Getman, I'll get you to do this because you always owe us a little more time than everybody else. If you would give everybody one of these, and then when they're through, throw them in the envelope and take them down, Getman. Take them down the last door on the right and dump them on the lady's desk, give them to her. Davis. Just checking, seeing who's late. No. I had a half a dozen things, but I just thought that's one I'd tell you about. With any luck at all, I'll get everybody knowing how to at least do that one because you've been forewarned. Is there an influence line problem? Yeah, you know it. Is there a...
PQ system?
Huh?
P system, Q system?
Well, that's what we just did.
Yeah.
Go ahead.
Green.
I know green. One of 2.